Hello everyone. We were discussing laws of motion. In that we discuss Newton's first law, second law and third law, and also how to deal with non-inertial frames in case of Newton's first and second law, how there is a pseudo force which comes up when we need to deal with non-inertial frames. Now we will deal with how to apply these laws in solving problems and solving real life problems. Okay, before doing that, let's understand what is a free body diagram. There is a concept called free body diagram. Let's understand what is that. Free body diagram. So any object in this surrounding, any object is not isolated. It is a part of a system. It might be part of an attached system. It might be part of a multiple body system. It might be part of any system. So free body diagram basically means a diagram where we will isolate that object and only indicate the actions and reactions on that particular body, right? Let's understand by an example. Let's say this is a system, this is a pulley, right? And there is a string which goes through this pulley which holds two objects. Let's say the mass of objects are m1 and m2, right? Now these two bodies will undergo acceleration if there is a mass difference, right? If the masses are same, there won't be any acceleration. But if there is a mass difference, let's say if m2 is greater than m1, so this body will come down and similarly this body will go up with the same acceleration. Now these two are connected through a string and it is a connected system, right? Now if I need to draw a free body diagram, I need to extract m2 separately, m1 separately, and indicate the forces acting on them and also indicate the direction of acceleration, right? Let's understand how. So for m2, what are the forces acting on m2? So gravity is everywhere. So gravitational force is one of the force which is acting on m2. So first is the, let's say w2, which is the weight or a gravitational pull. Next is the tension force because of this string, right? Again for m1, w1 and t, since the string is same, tension is same, right? Now if I need to draw a free body diagram for m2, it will come like this. This is m2, this is w2, this is t, and the final acceleration is in this direction. So I have freed this m2, I have isolated this m2 and brought out and indicated the forces. For simplicity, this is what is called free body diagram, right? Now using this free body diagram, I'll be able to appreciate the Newton's second law here, and I'll be able to write the force equation. We know that net force is mass into acceleration, right? So net force on m2 will be equal to what? Mass which is m2 into acceleration a. So what is the net force? You see, w2 is in downwards, t is upwards, and final acceleration is in downwards. So w2 is greater than t, which means w2 minus t, which is net force, equal to m2a. So using this free body diagram, I am able to write the force equation. Similarly, I can do for m1 as well, and I'll be able to find the acceleration. So again, recapping the same, for m2, there are two forces acting on it. One is the gravity, one is the tension. So I have separated it out, indicated the forces, indicated the direction of acceleration, and written the force equation. This diagram, where I have isolated the m2 from whole system and indicated the force, individual forces acting on m2 standalone, is called as a free body diagram, right? And it helps me simplify these complex networks. There can be more complex network, but I can go one by one by taking one at a time, right? Okay, let's see by one more example. So let's say these are two surfaces inclined at some angles, right? These are surfaces, right? And if I place a body, right? If I place a circular body maybe of, let's say, mass m in between these two, right? Now I need to make a free body diagram for this m, right? So what are the force acting on m? So you see, let's say this is surface S1, this is surface S2, right? So this surface S1, there is a contact with M. So whenever there is a contact between two bodies, there exists a normal force, normal reaction which we say. we dealt this with in the forces chapter, right? So there will be a normal which is n1. Here also there will be a normal which is n2. And obviously gravity is everywhere. So gravitational force W, right? So now, if I need to make a free diagram, let's say if I indicate M using a point, right? Let's say if I indicate this M using a point. So forces on M are, this is N1, then N2, and then W. These are the three forces coming up. And using this forces and by taking its component along different direction, I can find acceleration along X, acceleration along Y, right? As of now, I have not considered the angle, but we can do that. This is just to explain how can we draw the free body diagram. Let's understand by one more example. So let's say there is a surface and it has three different masses on it. M3, M2, M1, right? Now I need to draw free body diagram for all of these. All of these, right? How it will look like? Now first of all, gravity is everywhere, right? Gravity is everywhere. So gravitational force will come for all three separately. But what is different here? So you see, there are three contacts if you can see. Here is one surface to surface contact, here is one surface to surface contact, and here is one surface to surface contact, right? So there will be existing a normal reaction everywhere, right? So let's say M2 applies a normal reaction N1. So M1 will also apply N1 to M2. Same, third law. Let's say M3 applies to M2 as N2. So M2 will also apply N2 to M3, right? And let's say this surface apply N3 to M3, and M3 will also apply N3 to the surface. We are not worried about surface. So let's draw for M1, M2 and M3 separately. So if I bring out M1, so what are the forces? First is W1, which is gravity, M1G, and then N1. What about M2? M2 you see, M1 is applying N1 to M2, so N1 will come down, and M3 is applying N2, so N2 will come up, right? For M3, surface is applying N3 in this direction, and M2 is applying N2 in this direction, right? So this is the segregation of all three objects and their respective free body diagrams. Now, in any direction if I need, I'll be able to find acceleration, I'll be able to write force equations very simply, correct? So this is what is the concept of free body diagram, and this helps to explain, solve multiple complex these networks whenever there are multi-body networks, right? Next topic is the concepts of equilibrium, right? Concept of equilibrium. Again, equilibrium as the name suggests, right? As the name suggests, like you would have studied this terminology in your chemistry also. What is equilibrium? Where rate of a reaction forward and backward becomes equal. So in physics, when we talk about equilibrium, we basically say that system is in stable state and system has no acceleration, right? System is not accelerating. So if it is at rest, it will be at rest. If it is moving at some velocity, it will be moving at the same velocity. Basically means that there is no acceleration and hence there is no effect of force, right? So if sum of forces on any body, right, net sum of all the forces acting on any body, if that is 0, we say that the body is in equilibrium, right? Let's say for an example, very simple example. Let's say this is a surface, there is a block placed here, right? There is a block placed here. So what are the forces on this block if I make a free body diagram? One is the normal, another is the mg if the mass is m, right? So along this direction, let's say this is y and y dash direction, there is no movement, right? The body is still at that position, there is no acceleration, there is no velocity. So basically means that the body is in equilibrium. And if it is in equilibrium, sigma of force along y will be 0. Net force along y will be 0. So normal and mg is opposite to normal, so normal minus mg will be 0, so normal will be equal to mg. So this body is in equilibrium in y direction. We can't say about x as of now, but yeah, we can say about y, right? Let's understand by one more example what exactly is equilibrium. For example, let's say this is a rod, right? This is a rod which is placed in between these two perpendicular surfaces. Let's say the surfaces are S1, S2, and this is a rod, right? And rod is stationary. Rod is stationary. Now what does that mean? Rod is stationary basically means that whatever be the net force acting on this rod from the whole system is 0. We need to consider the rod as a whole and this whole system, right? And we need to say that the net force on this rod is 0. So what are the forces acting on this rod? So see, there are two contacts here. One is from S1, one is from S2. So there will be two normal reactions. N1 is the one normal reaction. N2 will be the another normal reaction. You can see why the direction is perpendicular. Normal reaction is always perpendicular to the surface. Now we know that gravity is everywhere. So third will be W, which is equal to mg if m is the mass of rod, right? Now when we talk about equilibrium, right? So this is an equilibrium. So this is an equilibrium basically means that there is no motion in any of the planes, not any of the planes, but along any of the axes. So there are two axes to this. This is a two-dimensional kind of format, right? You see, it can have motion in both the directions, right? So it can displace along x also, it can displace along y also, right? So basically, if it is in equilibrium, there won't be any acceleration in both the direction. And you can also see there are coplanar force acting on it. Forces along multiple directions. You see, this N2 is along x, N1 and W is along y, right? So if coplanar forces are acting on a body, but still the system is in equilibrium, basically means that the resultant of both the direction forces, resultant of force along x is also 0, resultant of force along y is also 0. And if this condition is met, then we can say that the system is in equilibrium under the influence of this coplanar forces, right? Now if I need to write how these forces are related, let's say if I talk about sigma Fy equal to 0, I can simply write that N1 minus W equal to 0 along y, since it is in equilibrium along y also. What about along x? So along x there is N2 here, right? Along x there is N2. But you see there is no other force coming up. But there are forces which we have not discovered as of now. But let's say there is some force here which can be a frictional force. We will discuss later on. So N2 minus F will be 0 in that case. So N2, normal reaction 2 will be equal to the frictional force at this. So there can be a frictional force here as well. So frictional force we will discuss in detail, but you just understand it basically opposes the tendency of motion. So this end has tendency to move forward, so frictional force is acting opposite, right? So and this end has tendency to come downward, so friction will act to the upward. So I have just explained this to make you understand how to deal with these coplanar forces in case of equilibrium, right? So let's solve a problem to understand the concept of equilibrium more. So the problem states that an object is in equilibrium under 4 concurrent forces which are shown in this diagram. We need to find F1 and F2. So there are 4 concurrent forces. Basically force acting at one point is the concurrent force. So let's say this O is the object or a point object which is in equilibrium, and it has influence of 4 forces on it. F1, F2, 4 Newton and 8 Newton. 2 are given to us, 2 are not given to us. And we need to find what is F1 and F2. So again, this is a type of coplanar force because force is acting in 2 different directions, right? Force is not unidirectional. It is acting in multiple directions. So we need to take it axis. we need to take it axis by axis, right, and understand. So let's take the reference axis for us is like this. As the standard, let's say x and y, right, like this. So F1 is along y, 8 Newton is along x, but these two are not along anything, so we need to resolve. You know, resolution of vectors. So you need to resolve them along both the axes. So this 4 Newton, if it is resolved along this becomes what? 4 cos 60, right? Perpendicularly, if I resolve this becomes 4 sine 60, correct? And if I resolve this F2 along this becomes F2 cos 30 along x, and along y minus y it becomes F2 sine 30, right? Now if I make a free body diagram for this object along x and y separately, I can see, you can see along x if I draw. So along x it is 8 Newton this side, 4 cos 60 positive x side, and this is F2 cos 30 in the negative x side, correct? Now, you know, since it is in equilibrium, sigma net force along x will be 0. So I can write that 8 plus F4 cos 30 60 minus F2 cos 30 is 0. Why minus? Because this is anti-parallel and at 180 degree to all this. So 8 plus 4 cos 60 is nothing but 2 will be equal to F2, and cos 30 is root 3 by 2, right? So F2 becomes what? 20 by root 3, or I can write like that, 20 by 3 root 3. F2 is 20 by 3 root 3. Now again along y also it will be 0. Along y also net force will be 0. So let's say if I take this problem along y also separately. So along y, if you see, this is F1 here, then there is 4 sine 60 also in the same direction, positive y, and then there is F2 sine 30 in the negative y. Now if I write the equations, I say that sigma of Fy will be 0 since it is in equilibrium in both the directions. Now F1 plus 4 sine 60 minus F2 sine 30 will be 0. Now F1 plus 4 into root 3 by 2 minus F2 is 20 by root 3, or 20 by 3 into root 3 into sine 30 is 1 by 2 will be equal to 0. So what is F1 now? F1 becomes 10 by 3 root 3 minus 2 root 3, right? So this becomes 4 by 3 root 3. So F1 is 4 by 3 root 3, F2 is 20 by 3 root 3, and these are the values of F1 and F2 to make this body into equilibrium along influence of the coplanar forces. So next topic for us under equilibrium is the Lami's theorem. So Lami's theorem is a theorem which takes into account the 3 concurrent forces on any point object. So let's say there is a point object O, and it is under influence of 3 concurrent forces. Basically means that 3 direct forces applying on O, which is F1, F2 and F3, inclined at some angles to it. Then these 3 forces has a direct relation which is given by Lami's theorem, and this can be used directly to solve multiple problems. We will not talk about derivation here, but yeah, we will just talk about the direct expression. The expression is F1 by sine alpha will be equal to F2 by sine beta, and which is equal to F3 by sine gamma. Now you see, alpha is the angle which is opposite to F1. You can remember it like that. Alpha is angle which is opposite to F1, so F1 by sine alpha. Beta is the angle opposite to F2, and gamma is the angle opposite to F3. So you can remember this expression to solve a problem where you have a point object and then you have 3 concurrent force acting on it. You can directly use this expression to find the relation between the forces in a state of equilibrium. So basically these 3 forces are making O2 the state of equilibrium, means there is no motion, there is no acceleration, and net force is 0. The resultant force is 0. Right. So let's solve one more problem on the topic of equilibrium, and also which will relate to the equation of motion. So the problem states that 2 bodies of masses m1 and m2 are connected as below. You see there is an inclined plane, m1 is on the inclined plane, m2 is hanging in the air. It is connected through a pulley. This is a pulley, a common string which holds both M1 and M2, M1 being on inclined plane, M2 being on air. And the whole system is on rest. Basically means that the system is not moving. And then we can interpret the system is in equilibrium, right? We need to find angle of inclination. What is theta? So what should be the theta so that this M1 and M2 are in equilibrium to each other, right? So before dealing that, we need to draw free body diagrams. Free body diagrams. Now, let's first indicate the forces, then we'll separate them, right? Let's understand for M2, the downward force is the gravity M2G, which is the weight. Upward force is the tension. So here also the tension will be same because the string is same, right? For M1, the downward force will be M1G. M1G, right? Now, I can draw free body diagram for M2 separately. For example, M2 will come here. I'll indicate T. I'll indicate M2G. Since acceleration is 0, I'll say that tension equal to M2G because net force, sum of net force will be 0. So tension becomes equal to M2G. Let's say this is equation 1. What about M1? Can I write a direct relation like this for M1 also? No. Tension is in this direction. M2G is not even perpendicular to it. It is at some angle to it. So I need to take components here again. So you see, this angle is theta. This angle is 90 and this is 90 minus theta. So if I draw perpendicular, this becomes theta again. This is perpendicular to the surface, right? So if this is theta, this component of mg will be mg1 cos theta, and this component will be m1g sin theta. M1g sin theta. And along this direction, there is no acceleration for M1, right? So if I draw free body diagram for M1, it looks like this. There is a tension, and then there is a M1g sin theta, and it states that tension equal to M1g sin theta. Now can I relate these 1 and 2? Both tensions are same since the string is same. So M2g is nothing but equal to M1g sin theta. Sin theta is M2 by M1, and theta becomes sin inverse M2 by M1. Now you can say that if you maintain this inclination as sin inverse of M2 by M1, as long as you maintain that, this system will not move and it will be stationary. But if we deviate, the system will come under acceleration, right? So we saw what is a free body diagram, how to draw a free body diagram, what is the concept of equilibrium and how to use it using Newton's laws of motion. Now from next lecture onwards, we will solve multiple problems on this type of problems, which will involve different concepts of free body diagrams, Lami's theorem, Newton's laws, pulleys, everything, and we will get more understanding of these topics, right? Till then, thanks.